Welcome to Saravji's educational talk about feature selection and feature engineering. In this part, I'm going to be going through the demo notebook about feature engineering. Like the other notebook, it's the same setup, starting out with functions and loading everything up. I'm starting where we ended up in the last notebook, using Baruta, the heuristic Baruta, to actually create a selection of features that we want to keep. So I'm running the Baruta package here, and next I'm taking a closer look at the selection that Baruta actually found. So here I'm looking at correlation matrix and see how everything works together. It looks a little bit convoluted. And there is the one or the other feature in here that actually does not look quite right. This is actually 204 here, so it seems to be not correlated very much to anything. So something seems a little bit off here. So nonetheless, let's create a baseline, a first experiment, running a baseline, taking this selected, sub-selected feature set and run it against our algorithms like we had. And so again, we're ending up with a nice solid performance with an MCC of 0.76, runner-up 0.76, so nice and solid. Yeah, looking at feature importances, we see that actually the 204 that we have in here doesn't come up. So using a random forest classifier and ranking the top 31s, going down here, we see a repeat of a lot of the features that Baruta selected, but we are not actually seeing this 204. So something seems to be a little bit off here. So what I'm doing here is I am selecting the 20th most important one here out of the random forest classifier that is not already in Baruta, in the Baruta subselection, or the first one actually that is not in the Baruta subselection in here, and I replace the 204 with this 455. Looking again at the correlation matrix, we see that it is a little bit busier, so we don't have a non-important feature in there anymore. And if we are actually regrouping those features, this is exactly the same features, just regrouped the correlation matrix. We're actually seeing that it appears that a lot of the features are very, very similar, or basically identical. So using this again and run it with our untuned algorithms, default setting algorithms, untuned algorithms, we get an MCC that is already approaching the 0.8. So we are at 0.793, which is nice. So having an additional look at the features, or those sub-selected features, we actually see how they are distributed and what we can see here. And there is very distinct patterns are emerging here. So we have the double humps here, we have normal distributed here, then we have the little bit skewed ones here, and that is basically all the variations that we are seeing here. So it seems to be very uniform how the features are looking like. And using this arrow bar plot here and to actually check how our features are distributed, we can see that they are all very close with around the values, the same values, but that the spread is wildly varying. So The one thing that I'm doing here for the feature engineering, for the first step after we have done a little bit of manual cleaning up of the feature selection and reselecting the features, I am scaling the features, so to kind of equalize them from here. So there is a couple of methods that are in the standard toolkit, scikit-learn toolkit. So one is the standard scaler, so using standard scaler and then again running it with the subselected features, then scaled data, and using the default settings in the algorithms and running this. We are already pushing closer to the 0.9 in the on the MCC, so we are getting a 0.86 here. The runner-up is 0.82 here. So we're starting to get a really nice solid performance. So let's try the min-max scaler as well for the feature engineering. So the sub-selected features set that we are using, and using the min-max scaler to scale the data and rerunning the experiment. And we are ending up at 0.83, so also a nice improvement, nice solid improvement over the baseline that we had. So there seems to be something solid about the using a scaler. So next step is actually using PCA. So going back to PCA, the reason being, if you remember here, we have 1, 2, 3, 4, 5, and those here are kind of looking inverse to the other ones. So we have a few very distinct patterns in our features. So using PCA to actually reduce the dimensionality of this data set could yield something. So let's try this out. So reducing the 20 features to 5 dimensions. So just plain PCA. So it's the sub-selected features in the data set, no scaling, doing a PCA to reduce the dimensionality of the data, and then again using the untuned algorithms to in this experiment. And this way we get the 0.77, which is a slight improvement over our baseline. So PCA seems to be doing something here. So let's try PCA with the scalars. So PCA as well as scalars to see what we can do with this feature subselection. And here we are again ending up with nice solid performance around 0.86, which is about the same as what we had with the standard scaler. And also with the min-max scaler, so it's 0.82. So it's a nice solid performance what we get here. In these experiments, I applied PCA first, and then I was using scalar. Now, the next experiment is actually applying a standard scalar, then applying PCA, and then rescaling the reduced dimensionality feature set that we have. And then I'm using tuned algorithms as well. So there is quite a bit of time in here, time investment to actually get to those tuned algorithms. But this is basically how far you actually can push those results, and you get about a nice solid 0.86. So to recap, And we get, with our baseline 0.63, then manually going in there and verifying the features and doing a manual features post Boruta feature selection and verifying that everything is fine there. We are getting a nice improvement here. Using standard scaler, we are pushing it nicely. Min-max scaler doesn't do bad either, also too bad. PCA is not quite as good. It doesn't improve it as much. Then using combination of standard scaler and PCA in the sequence, we are getting 0.857 min-max scaler. The PCA, we get this performance. And then actually really spending some manual time in here and fine-tuning this whole solution. We can push it a little bit higher, 0.863, compared to the 0.86 with just the plain standard scaler. So in this way, we are actually not able to get this much more performance out of it than compared with a standard scaler. And again, the standard scaler, and this experiment with standard scaler, is an untuned algorithm. This is the algorithm how it is coming out of the bag, and this one here is just pushing the algorithm here with the tuned algorithm really further. So there is a lot of time difference that I actually needed to invest to push it from this 0.86 to this solution 0.863. And with this, I am concluding this video about the demo notebook feature engineering, and continue on in the rest of the talk with all the learnings and the results in a nice overview. Thank you. So let's recap the results of feature engineering. We are using MCC as evaluation metric, and the baseline using default models. Our MCC was about 0.76 in just shy of 2 minutes. Then next we did a deep dive, actually looking at the individual features that our heuristic produced and do some soundness checks on there and modifying it a little bit. With this, we actually could boost the MCC to 0.79, and the runtime, because we were still using default models, was just shy of 10 seconds, but we actually needed to put the time in to evaluate it. Next experiment we did, we used the standard scaler to, on the modified feature selection that we had out of the deep dive, to equalize, to engineer and scale the features so that they are actually comparable importance and so on. And with this we could actually boost our MCC to 0.86, and using the default models, the runtime was still below 10 seconds. Next experiment was using the min-max scaler instead of the standard scaler. Same idea, different scalars, different scalar approach. Our MCC was 0.83, and runtime again just shy of 10 seconds. Next experiment, we were using PCA instead of a scalar on the modified feature selection, again with the default models, and with this approach our MCC actually dropped to 0.777, so it was less than what we had after the deep dive. Running again the default models, runtime is a little bit less than 10 seconds. Next experiment was combining standard scaler and PCA on the modified feature selection using default models, and our MCC was 0.857 in a little bit less than 10 seconds. Next experiment was using min-max scaler plus PCA, again on the modified feature selection using default models, and our MCC ended up at 0.824. So at this point we have not improved anything beyond what we actually could do with the standard scaler. And then the final approach was standard scaler, PCA, standard scaler on the modified feature selection, and then actually very carefully hand tuning the models. And with that I was able to push the MCC to 0.863, so 0.003 better than just standard scaler. The time that actually went into this last part are a lot of hours compared to what the standard scaler was, just to get this 0.003 in the MCC score in improvement. The runtime itself is less than 15 seconds. To put this into perspective, what this MCC value actually means. So comparing the results of 0.86 and 0.863 means that 43 and respectively 41 incorrectly classified observations, or an error rate of 7.167% or 6.83% respectively, are in the prediction. Now it is important to understand this data set, and what this means is that we are around 1 or 2 observations incorrectly classified that are in the data set. So the data set actually has included errors in the prediction. So there are deliberate errors in this data set. And the results that we are seeing here are basically finding those induced errors in the data set. That is kind of the level of performance that we're looking at here. And looking at this, yes, feature engineering is making sense. You can really push last little bit details. The question is, how much effort is it worth it? So I'm not saying no feature engineering at all. Definitely feature engineering to really push the envelope. But does it really bode well? Is it time well spent to really overdo it to the max? So there is experience necessary to know how far to go. Definitely going down the road. The question is how far. And I hope that I can give an intuition with this, that yes, in this case, trying out a few relatively basic things for feature engineering is fine. And then when we are actually starting to see that, yeah, we can't push it that much, relatively easily, that much further, then it's probably time to call it good enough. With this, I'm concluding this part. See you in the last part.